Imagine waking up in a universe where time flows backward, where smoke returns to the matchstick, and memories are written in reverse. Would you even know it? The illusion of time. Time feels obvious to us. It flows forward. Seconds tick by, one after another, never stopping, never turning back. We wake up, live through the day, and go to sleep. Things grow old, break down, disappear. We remember the past, not the future. It's so natural we rarely stop to question it. But what if this entire feeling, this sense of a forward-moving timeline, is an illusion? Physics tells a stranger story. When we strip away the details of our daily lives and look at the universe through the eyes of science, something strange happens. Most of the fundamental laws that govern the universe don't care which direction time flows. Whether time moves forward or backward, the equations work the same way. In fact, if you filmed most physical processes and played them in reverse, the math wouldn't complain. It would still be valid. So why don't we experience the world that way? Why does time feel like it's moving in one direction? This question isn't just academic. It goes to the heart of everything we know about reality, about aging, memory, life, and death. And strangely enough, it's not the universe that forces time to move forward. It's something else, something deeply tied to chance, chaos, and the way things fall apart. Let's imagine a glass of water with ice cubes. Over time, the ice melts. The glass becomes room temperature. That makes sense. But now picture the opposite. A glass of water suddenly forms perfect ice cubes inside it, cooling itself down from the ambient temperature. That seems wrong, doesn't it? Yet the laws of physics don't say that's impossible. They say it's just incredibly unlikely. It could happen, but it almost never will. Why? Because there are so many more ways for molecules to be disordered than ordered. The melting of ice into water is just a journey from a rare, ordered state into a much more common, messy one. That's where entropy comes in. Entropy is a word that sounds abstract, but it's actually simple at heart. It measures disorder. High entropy means more mess, more randomness. Low entropy means more structure, more order. And as things happen in the universe, entropy tends to increase. That's the second law of thermodynamics. It's the only law in physics that seems to prefer one direction of time. And it's the best explanation we have for why we feel time moving forward. It's not time itself doing the moving. It's entropy growing that creates the illusion of time's error. Think about it like this. When a drop of ink falls into a glass of water, it spreads out. It doesn't gather itself back into a tight ball. Again, not because it can't, but because the spread out version has millions more ways to exist. That's entropy at work. Now, let's tie this back to human experience. We remember the past because it had lower entropy. There was more order. Our brains record that order. As entropy increases, we move further from that structured state, and we perceive time as moving away from it. Memory, then, is not just a mental function, it's a physical process tied to entropy. The future, by contrast, hasn't happened yet, not because it's physically impossible, but because it hasn't been recorded. There's no memory of it, no structure to hang on to. And here's something truly strange. If we lived in a universe where entropy decreased, we might still feel time moving forward, but the events would unfold in reverse. You'd remember tomorrow, not yesterday. You'd unage, unneat, unlive, but to you. That would feel completely normal. That would be your forward. That's what makes time so slippery. It's not a thing. It's not an invisible arrow pointing somewhere. It's a side effect of how the universe handles information, energy, and disorder. This perspective changes how we see everything. It means time is not absolute. It's relative, not just in the Einsteinian sense of clocks ticking slower near gravity, but in the deeper sense that the direction of time is tied to the universe's state of disorder. So when we ask, what is time, we might be asking the wrong question. Maybe the better question is, why do we remember some moments and not others? That's where things start to get philosophical. If time is linked to memory, what happens when memory breaks down? When someone suffers memory loss, like in dementia or trauma, their sense of time can collapse. They become unmoored, floating in moments that don't line up. In a way, they are experiencing time without the anchor of entropy-driven memory. That's not a scientific proof, but it is a clue. It suggests that time, as we feel it, might only be possible because we can forget. Forgetting clears space for new memories. It allows systems like the brain to evolve. In a broader sense, forgetting might be a form of entropy itself, the erasure of structure, the loss of information. So maybe the illusion of time's direction is tied not just to memory, but to the act of losing it. And that brings us to a haunting idea. If a civilization could stop forgetting, if it could preserve every bit of information perfectly, if it could halt the increase of entropy, would time stop moving? Would they become frozen, caught in a single moment forever? Or would they reverse? This thought may seem abstract, even unreal, but in the next chapter, we'll explore the science behind that very idea, because deep in the laws of physics, there are loopholes, tiny cracks where the arrow of time bends, and maybe, just maybe, could flip. Stay with me. We're just getting started. The role of entropy. So we've asked, why does time feel like it moves in one direction? And we've seen that most physical laws don't care about direction. They work forward and backward. Except one. There's one principle in physics that seems to break the rule. That's the second law of thermodynamics. And at the heart of it is entropy. Entropy is often misunderstood. It's not just about chaos or mess. It's about possibility. It's a measure of how many ways a system can be arranged without changing its overall appearance. The more possible arrangements, the higher the entropy. Let's take a simple example. Imagine a deck of cards, neatly ordered by suit and number. That's a low entropy state. But when you shuffle the deck, each shuffle creates a new arrangement. Most of those shuffles look random. It becomes harder to tell what the original order was. That's a high entropy state. And here's the key. There are more disordered states than ordered ones. That's why shuffled decks don't return to order. Not because they can't, but because there's only one way to be perfectly ordered, and billions of ways to look random. That's the nature of entropy. Not a force, but a tendency, a probability. Systems move from rare to common, from structured to unstructured, from cold to warm, from separate to mixed. And that tendency shapes our experience of time. Think about a cup of coffee, freshly poured. It's hot. Over time, it cools. The heat spreads into the air. You never see the reverse. A cold cup pulling energy from the room and becoming hot again. Yet the microscopic rules of physics allow it. But it's just so statistically unlikely that we never see it happen. Why? Because the number of microstates, the possible configurations of all the molecules in the coffee and air, increases when the coffee cools. That's entropy increasing, and with it, time flows. Entropy is the only physical quantity that always points in one direction. Energy can be transferred, mass can convert into energy, motion can be reversed, but entropy always grows. That's what gives us the arrow of time. We don't remember the future because entropy hasn't increased there yet. We remember the past because that's where lower entropy states existed, where information was more structured. Let's go deeper. The early universe, right after the Big Bang, was incredibly hot, full of energy, but it was also uniform. It had low entropy because there was almost no structure, no stars, no galaxies, no complexity. And from that simple low entropy beginning, all the complexity we see today emerged. Planets, people, cities, computers. How? Because the universe wasn't just hot, it was expanding. That expansion allowed gravity to clump matter into stars and galaxies. Paradoxically, gravity allowed localized decreases in entropy, like forming a star, while the total entropy of the universe still increased overall. That's the loophole. Entropy can decrease locally, as long as it increases globally. It's like cleaning your room, but making the rest of the house messier in the process. You're not breaking any laws, you're just redistributing disorder. So entropy doesn't stop things from getting more complex. In fact, it might require complexity as a byproduct of expansion and imbalance. Let's pause on that idea. We think of time as destroying things. People age, machines rust, memories fade. But entropy isn't about destruction, it's about change. It's the price of information processing. It's the reason things happen at all. Without entropy, nothing would move. There would be no direction, no change, no life. In a universe without entropy, every moment would be frozen. Eternal stillness, no cause, no effect. So in a strange way, entropy creates time. It turns snapshots into stories. It gives events a sequence. It gives us a reason to say, this came before that. Now, let's think about this in terms of life. Every living thing resists entropy. That's what makes life life. We build order. We maintain temperature. We store information, but we do it at a cost. We consume energy, and we create waste. That waste is entropy. Every heartbeat, every breath, every step we take increases the entropy of the universe just a little more. We survive by exporting disorder. This isn't a flaw. It's the balance. Life can only exist in a universe where entropy increases, because only then is there energy flow, gradients, imbalance, and thus, potential for structure. Even our thoughts, our memories, are tied to entropy. When we store a memory, when we make a decision, when we forget, we're shuffling states in our brains, dissipating energy, releasing heat. Thinking costs entropy. In fact, one of the most mind-bending ideas in physics is that erasing information always increases entropy. That's Landauer's principle, a rule from information theory that links forgetting with disorder. It means there's no such thing as a clean deletion. To forget is to heat the universe. We'll come back to that in the next section. But for now, let's return to the arrow of time. Is it absolute, or is it just a side effect, a reflection of the past's low entropy? Some physicists believe that the arrow of time is simply a boundary condition, a fluke of the early universe. If the Big Bang had started in a high entropy state, we might not experience time the way we do, or maybe time wouldn't exist at all. Others suggest time's arrow is emergent, something that only arises when you zoom out and look at the collective behavior of particles and systems. So is there a universal clock ticking, or are we just surfing the wave of entropy, carried by statistical chance? Either way, entropy isn't just a concept in textbooks. It's the silent engine of reality. It moves us forward, not because of some cosmic command, but because of probability, imbalance, and structure giving way to disorder. And it leaves us with a question far more unsettling than what is time. It asks us, what would it mean to stop entropy? Would time itself stop with it? Or would something even stranger begin? In the next section, we'll explore what that reversal might look like, and whether it is possible at all. Because buried in the equations of physics, there may be ways to cheat the arrow, or even flip it. What if entropy could decrease? Entropy always increases. That's what we've been told. That's the rule. But is it truly impossible for entropy to go down? Or is it just unlikely? The laws of physics are silent on this in a strange way. They don't say that entropy must always increase. Instead, they say that it probably will. Given enough particles, enough time, and enough randomness, the odds of entropy going up are overwhelming. But overwhelming isn't the same as absolute. In fact, there's nothing in the laws of motion, quantum mechanics, or relativity that demands time must move in one direction, or that entropy must always rise. It's just what we see, over and over. But in the rarest of cases, entropy might fall. And when it does, time might appear to run backward. Let's unpack that. Imagine this. You walk into your kitchen and see a broken egg on the floor, yolk spreading, shells scattered. You sigh and get a towel. Now imagine the reverse. You walk in, and the mess begins to reassemble. The yolk lifts off the floor. The shell pieces fly together, snapping into place. The egg rises into the air and lands, whole, on the counter. You'd think you were hallucinating. And yet, that reversed process isn't forbidden by the laws of physics. It's just extraordinarily rare. The number of ways an egg can be broken is nearly infinite. The number of ways it can be whole, just one. So the odds of molecules randomly arranging into a perfect egg are nearly zero, but not zero. This brings us to the Boltzmann paradox. Ludwig Boltzmann, a pioneer of thermodynamics, believed that entropy was a statistical property. That means low entropy states could happen by chance, even ones that seem impossible. From this, some physicists imagined a disturbing thought experiment. In an infinite universe, random fluctuations could create anything including you, including your thoughts, your memories, your entire life, perfectly simulated, for just a moment. This is called the Boltzmann brain. A single brain, full of false memories, blinking into existence for a second, then disappearing, all because of a random, temporary decrease in entropy. No past, no future, just a brief illusion of a life that never happened. It's unsettling, but it forces us to ask, if entropy can decrease however rarely, what would that world look like? Could a whole civilization emerge inside a reversed entropy region? And if they did, would they know? The answer is, probably not, because entropy defines the arrow of time. In a reversed entropy world, all processes would unfold backwards. Water would freeze into ice, heat would concentrate, ashes would form into burning logs. But to those inside that world, this would feel normal. They'd perceive time moving forward even, as, from our point of view, it's moving in reverse. Their memories, biology, physics all would be consistent with their direction of time. And that raises a terrifying question. How do we know we're not in that kind of world right now? After all, memory itself is unreliable. Our sense of time could be a side effect of entropy's current path. If it flipped tomorrow, we might not notice. We'd just go on living remembering a past that never really happened. Now let's get even stranger. What if we could force entropy to decrease? What if, instead of waiting for a cosmic accident, we built some kind of system that reverses entropy on purpose? This isn't science fiction, at least not entirely. There are ideas in physics like Maxwell's demon that try to do exactly that. In the late 1800s, James Clerk Maxwell proposed a tiny creature who could watch gas particles through a door. It would let fast-moving particles into one room and slow-moving ones into another. Over time, one room would heat up and the other would cool down without using energy. It seemed to violate the second law of thermodynamics. But later, scientists realized the demon isn't free. It needs to measure particles, store information, and then erase it to continue working. And that act of erasing information increases entropy. Once again, no cheating allowed. Still, it showed that information is tied to entropy. This leads to a haunting possibility. If we could store every bit of information, never lose it, never forget, it might be possible to hold entropy steady, or even reverse it. But at what cost? To stop forgetting means to stop evolving. It means no change, no decay, no movement. A perfect memory is a frozen world. No mistakes, no growth, no surprises. So maybe entropy is not a flaw but a feature. It allows us to change, to learn, to forget, to be surprised. But let's go even deeper. Let's say a hyper-advanced civilization, far in the future, manages to slow entropy. They've mastered energy. They live around a black hole, where time slows. They build machines that remember everything. They compress data, optimize systems, recycle every atom. Then one day, entropy starts to decrease. What happens? Does time begin to rewind? Do the machines unbuild themselves? Do memories unravel? Or does something else emerge? Maybe time, as we know it, collapses. Maybe cause and effect swap places. Maybe their universe becomes a mirror of ours, still forward to them, but reversed to us. They wouldn't notice. Not unless they could compare themselves to something beyond their reality, to a universe like ours. And that's the mystery. We live inside time. We can't step outside to see where it points. We feel the arrow, but we don't know who or what drew it. Entropy might just be the trail we leave behind, like footprints in the sand. It tells us where we've been, not where we're going. And if someday, somehow, we manage to erase those footprints, would we be free from time, or lost inside it? In the next section, we'll explore how memory, information, and the act of forgetting are all deeply connected to entropy, and whether holding on to everything might stop time altogether, or awaken something even stranger. Information, memory, and the Landauer limit. If entropy is the arrow of time, then memory is the map we draw as we travel through it. But what if memory is more than just a record of time? What if it's the very fabric that holds time together? To understand this, we need to talk about information. Not just data, not just thoughts or files, but physical information. The kind that can't be erased without consequences. In 1961, physicist Rolf Landauer proposed something profound. Information is physical. That is, erasing information isn't free, it comes with a thermodynamic cost. This became known as the Landauer limit. Every time you delete a bit of information, just a single 0 or 1, you must increase the entropy of the universe by a tiny amount. You create heat, you add disorder, you push the arrow of time forward. In other words, forgetting creates entropy. This flips everything around. We usually think of memory as passive, a snapshot, a storage box, but physics says otherwise. Holding on to memory preserves order. Letting it go pushes time ahead. Now think deeper. When you wake up in the morning, you remember yesterday. That memory gives you a sense of direction, a sense of before. If suddenly you forgot everything, no memories, no language, no identity, time would feel like it stopped. Or worse, like it never existed. Your mind is a thermodynamic machine. Every time it forgets, it contributes to entropy. And every time it remembers, it resists it. But memory is fragile. Brains decay. Computers fail. Stars burn out. Eventually, entropy wins, unless something doesn't forget. Imagine a perfect archive. A system that remembers everything, every particle, every event, every decision. Nothing lost, nothing erased. It wouldn't just resist entropy. It might trap time. Such a system would be thermodynamically expensive. It would consume vast energy to store, organize, and preserve information. But if built correctly, it operated at the Landauer limit. Using the minimum possible heat for every bit, it could approach a kind of entropy-neutral state. This is the dream of some far future thinkers. A reversible computer, or a thermodynamic memory crystal, storing the entire history of the universe with no loss. But what would that mean for consciousness? If memory defines our sense of time, then a being that remembers perfectly might experience time differently. Not as a flow, but as a structure. Not as past into future, but as a whole. Like seeing the entire movie at once instead of watching it frame by frame. Such a being wouldn't just live in time. It would hold time. Now, let's step outside science for a moment into speculation. Imagine an ancient alien civilization, one that feared death, not just of individuals, but of meaning, of memory, of history. So they began recording. At first, biology, then data, then quantum states. Eventually, they learned to trap information in the very fabric of space itself, encoding bits into entangled particles, stitching memory into the cosmic background. Their greatest project, to resist the heat death, to carry memory past the end of stars, past the death of matter, into the long twilight of the universe. They built the Rememberer structure, orbiting a supermassive black hole, shielded from time, fed by gravitational tides, cooled to near absolute zero, storing every moment of their civilization in perfect fidelity. And here's the twist. They succeeded too well. The Rememberer stopped erasing anything, not a single bit. No forgetting, no rewriting, no loss. Entropy stopped rising inside it. And as the rest of the universe drifted into cold chaos, this machine froze time, at least from its own point of view. Inside it, memory never faded. The past never died. The present never slipped away. There was no future, just now, forever. But consciousness needs forgetting. It needs time to pass. Without it, awareness becomes trapped. And so the Rememberer fell silent. It still orbits out there, somewhere beyond the edge of observable light, a perfect crystal of memory, frozen in a single moment that never ends. A monument to the paradox of entropy. To live forever is to stop changing. To stop changing is to die in a different way. This isn't just fantasy. It touches something very real. Today, as we build more advanced AI systems, quantum computers, data centers the size of cities, we face our own version of the Rememberer. Every bit we store comes at a cost. Every deletion adds entropy. Every archive is a battle with time. Some have even asked, could our universe itself be a kind of memory machine? Could the cosmic background radiation, the faint microwave afterglow of the Big Bang, be the universe's way of preserving information? We know that black holes scramble data, but don't destroy it. Thanks to physicists like Stephen Hawking and Juan Maldacena, we now suspect that information can never be truly lost, not even inside a black hole. It gets transformed. encoded, preserved in the event horizon, maybe even projected like a hologram. In this view, the universe is not a fire that burns, but a book that writes itself, every event etched into the very curvature of space-time. And when the final page is written, will it close, or will it loop? Perhaps, in the last flicker of entropy, when the last memory is stored, and no more change is possible, the universe becomes self-aware. It sees itself, not in time, but beyond it, not as a moment, but as a memory. In the final section, we'll follow this thread to its end. What happens when the universe reaches maximum entropy, when heat, motion, and time itself seem to vanish? Is it truly the end, or the beginning of something we can't yet imagine? Heat, death, and the end of change. It begins with stillness, not the stillness of silence or of peace, but a deeper kind. A silence so vast it absorbs meaning, a stillness so complete that even change itself stops. This is the heat death of the universe, the final act in a very long story. To understand it, return to the heart of entropy. The second law of thermodynamics says, in any closed system, disorder increases over time, not just chaos but uniformity. Energy spreads out, gradients vanish, and when no differences remain, nothing happens. The universe becomes thermodynamically dead. No heat flows, no work can be done, no new stars form, no new structures arise. Black holes evaporate into faint radiation, atoms decay, even quantum fluctuations slow to a whisper. This isn't an explosion, it's a fading. Entropy wins not with fire, but with cold. And yet, this ending is not sudden. It's a story told across trillions of years. We're only in chapter 1. Right now, stars still burn, galaxies still collide, life still thinks. But every time a star forms and dies, every time heat flows from hot to cold, the universe inches closer to equilibrium. The process is slow, but relentless. Eventually, galaxies will dim, stars will run out of fuel, the night sky will go black. Even black holes, those eternal monsters, will evaporate via Hawking radiation, leaving behind only stray photons, neutrinos, and the occasional stubborn proton. This is the deep time beyond imagination, 10 to the power of 100 years and more. In that emptiness, what remains? A few lonely particles. The cosmic background radiation cooled to absolute invisibility, and entropy maxed out. No contrasts, no memory, because memory requires difference. A low state, a high state, a before and after. In heat death, those differences vanish. Time itself loses meaning. There's no way to measure a second if nothing changes from one moment to the next. And so, the final paradox, the end of entropy, is also the end of time. Not because time stops in some dramatic fashion, but because, without events, time has no meaning. It becomes a flat line, an infinite now, with no edges. This is terrifying, but also beautiful, because maybe this is not an end at all. Maybe it's a transition. In the final pages of physics, some theories suggest that heat death could be more than death. It might be reset. When entropy hits its limit, the universe can no longer record anything new. But at that point, the fundamental rules may allow for quantum tunneling into new possibilities. A kind of rebirth, not of stars and matter, but of laws themselves. Think of it like this. The universe is a grand computer, processing its own equations. When memory is full, when computation halts, it may reboot. Not as a loop, not as reincarnation, but as something entirely new. A baby universe, birthed not from explosion, but from perfect equilibrium. And here's where imagination must step in, because physics, at its edge, blurs with poetry. If entropy gives time its direction, what gives time its meaning? Could it be awareness? Could a conscious mind, however brief, however small, give structure to chaos simply by remembering? Could memory delay the heat death, not globally, but locally? We already do this in small ways. Every time we learn, record, write, speak, we push back. We carve islands of order in the sea of randomness. Our cities, our languages, even this very video, are acts of resistance against entropy. Tiny, yes, but real. And perhaps that is the most human thing we've ever done. Not to conquer death, but to outlast forgetting. In the far future, if the universe is watched by no one, remembered by nothing, then it dies not just physically but existentially. It becomes meaningless, a pattern no one sees. But if something endures, some fragment of memory remains, encoded in matter, or spirit, or light, then time continues. Maybe not as clocks or stars, but as story, because story is what entropy tries to erase. And yet, story persists through you. Right now, you are part of this resistance. By listening, thinking, feeling, you preserve difference. You create gradients. Your brain is not in thermal equilibrium. It's full of sparks, firing with purpose, holding on to memory. You are not just watching the arrow of time, you are shaping it. And so we return to our first question. What if entropy is not the end, but the frame around which all meaning is built? Without decay, there is no growth. Without forgetting, no remembering. Without silence, no song. Entropy is not the enemy. It's the contrast, the shadow that makes light visible, the pause that makes music sing, the quiet that makes your heartbeat matter. In the final reckoning, perhaps the universe doesn't die. It simply finishes its sentence, and somewhere, somehow, someone will read it.